So like I say, Hamiltonian hydrogen atom. This is what we're doing, quantum mechanics of hydrogen atom. The route that you've now seen a couple times is Schrodinger equation meaning the Hamiltonian, write it all out. This is painfully large. We're going to break it down into little pieces. It's so big you can kind of look at the parts and understand the parts. Then we look at the wave functions, and we can kind of break that down into parts too. The wave functions are getting kind of big at this point, and so we can look at them and understand nuances in like the various parts of the wave functions. Again, they're kind of big at this point. And then there's things like turning points. There's some quirkiness to it. You can also explain the periodic table. I talked about that last time. This will take about a week, and then we're done. After this is spectroscopy, which is relatively easy the way I do it. Kinetics, and seriously, we're almost out. Okay, so Schrodinger equation. One thing that has to happen because, you know, God, don't you miss this, right? Wasn't that easy? And this is how Schrodinger figured out kinetic energy works. But because atoms are round, we have to go to, oh sorry, this is called del squared. So this is called del squared. I have to introduce this notation. So this is kinetic energy. Del squared is the kinetic energy operator. You've seen this before, right, in your math classes, some of your physics classes. Right, second derivative in 3 dimensions tends to come up in a lot of mechanics and physics equations. So you've probably seen this before. I have to introduce this because it's just, otherwise I'm just writing things out for infinity, and you kind of hopefully should know what this is. Okay, now the reason I'm saying this for the beginning, I'll try to make sure that, you know, I don't want you memorizing. Now, I know you've seen it before, but I don't want you memorizing it, so I'll make sure it doesn't appear on any test. You know, I don't want you remembering what that symbol means. Not that it's that hard, but okay, now the reason that the Schrodinger equation can be a little bit difficult. Okay, mass electron, so when I say MELEC, that's mass electron. And I've got del squared for the electron. Okay, now this is why this gets painful, potentially painful. You got two things. You got two things that you have the kinetic energy of. So you've got a kinetic energy of, sorry, I keep wanting to write nucleus. Instead I'm going to write proton because that's really what it is. Okay, so you've got kinetic energy of an electron, you got the proton, because that thing is usually moving too. In fact, because of the uncertainty principle, and because the universe is finite, technically everything is always moving. And now here's the thing, we got a separability problem. R is the, I'm not going to specify this, you should know this. No, I'll write it down, I'm sorry, I'm going to write it down. I'll write it down, because there's been a couple of R's that haven't there. This is the proton-electron distance. Proton-electron distance, right? Okay, good, right, hydrogen atom, don't forget that. You know that a hydrogen atom is a proton-electron. Okay, so separability, guess what? Separability just got hosed in the process of connecting the proton and electron. Note that this is Coulomb's law. What am I doing? So I think I've made a mistake. I think that this is minus. I wrote plus, right? That's minus. That's minus because energy going, so remember that we ran into this with delta G last semester. Negative energy is technically good. We want to go downhill. That means changes in energy that are negative are good. So remember that Coulomb's law is charge 1 times charge 2. The electron's negative. And it also means that this is energy lowering. And that's the thing that captures the electron. So remember, if I have a particle in a sphere, it's captured because there's an infinite barrier. And I have a particle on a string, it's on a string. If I remove the barrier and remove the string, the particle's just going to wander off. It's actually a free wave. So there has to be a capturing potential if I've removed the box, and that's Coulomb's law. And it works, and you've got yourself a hydrogen there. Okay, now, normally I spend about a good 10-20 minutes on this. I'm not going to in this case because it's just kind of a nosebleed. But again, I want to point out that the Schrodinger equation, the Hamiltonian, has a cross term. and it's bloody, almost impossible to get rid of it. This R depends on the position of the nucleus and the electron. And that means you've got a separability problem, because what you really want to do, all right, so this is the Hamiltonian. What you really want to, of course, do is have two wave functions, one for the proton and one for the electron. If you can't separate them, then you've got a major problem. Now, instead of going through all the bloody math to show you, I'm just going to tell you what real quick what the answer is. So separability equals center of mass coordinates. Sorry for my shorthand. Okay, so just like now remember Maxwell-Boltzmann. If you looked at the homework, by the way, I did put up the homework. It was late on Wednesday. I did remind you about Maxwell-Boltzmann stuff because you do have a final that's really sooner than later. Maxwell-Boltzmann, we talked about center of mass coordinates when you have difficult problems. You can separate things in a center of mass coordinate and a relative coordinate frame, and that's the solution. So when you do that, you end up with a wave function for center of mass, which is basically the nucleus, the proton, and the other thing, the relative, which is basically the electron. And that's because the proton and the electron have very different masses. So, you know, like the reduced mass, right? The reduced mass is like 99% the proton, and the residual, of course, is 99% the electron. Because the proton is so much mass, it's 2,000 times heavier than the electron, this problem is really kind of a non-problem. You turn it into center of mass, and you get two different Schrodinger equations, one for the center of mass, one for the relative, but the relative is exactly the same of a hydrogen atom, of an electron, if you just pretended the proton wasn't there minus the Coulomb potential. As though the proton was stationary. So anyway, again, this takes us like 4 or 5 steps of algebra, and that's going to take 15-20 minutes. I just don't even want to bother, because all I'm going to end up doing is just writing down the Schrodinger equation with that, with this Coulomb's law, and it basically just states that the proton is completely immobile, and you know that's not so bad, right? I do want to point out one thing though, that this is something that a lot of people, physical chemists, even PhD physical chemists, like to forget this, or maybe they legitimately have forgotten this, that everything we've been doing is for an electron. Now, what I'm going to show you in the little video in the next hour, I show you an electron trapped in a 1 nanometer box. I'm going to show you how it escapes. And it escapes about, so it moves on about a 1 times 10 to the minus 16 second scale, right? So that is 0.1 femtoseconds. That's how fast it moves. Nuclear coordinates move on the order of about 1 times 10, hold on, I have to do it in my head, 15 minus 12 minus 11 seconds on a few picoseconds. So if we could watch a movie, now you're going to watch a movie of an electron. I have to represent it by a wave function because I have to. That's what quantum is. That's why you're in here. And you're going to see that it moves around on this time scale. Now, atoms, let's do, instead of a hydrogen atom, let's do an H2 molecule. And let's say that I wanted to show it rotating. I actually can just do that pretending as though it's like the baton of a cheerleader. I can just mathematically use Newton's law. And it's not that bad. Plus, my time step would be 10 to the minus 11, 10 to the minus 16. Now this also shows, now don't write this down, I'm just telling you stuff at this point. When it comes to modeling things, notice that I said that I have to do electrons with quantum mechanics, and I'm going to show you how that works in the next hour. But you can model the motion of molecules using just mass times velocity, using Newton's law. What if you tried to do both simultaneously? You have this major problem. Let's say that you want to model this thing rotating while the electrons are shared in between. You would have to spend So remember, this is a factor of 10 to the 5, not 5. It's not like, oh yeah, you have to simulate an electron for 5 steps, and then you can move the, yeah, you have to simulate the electron for a couple steps, and then you let the atoms move, then you let the electrons move, then you let the atoms move. No, you cannot do a computer simulation where you have 2 different things happening on these 2 different types of time scales. So again, if you want to meaningfully simulate electrons and protons moving, you have a gigantic problem that basically cannot be solved. Not with computers as we know them, not with quantum computers, it can't be done. We have no idea what the technology would be like to allow electrons and nuclei to move simultaneously because of this different time scale. What's kind of cool though is because atoms are so heavy, you can use like Isaac Newton mass times velocity mechanics. Physics mechanics equations work just fine. Except occasionally H plus. For H plus is light, it's just a proton. It has some quantum mechanical behavior in terms of its nuclear motion. Now again, electrons, I can't emphasize this enough, electrons are light and fast, and they must be treated quantum mechanically. You cannot do mass times velocity for electrons. It utterly fails. For nuclear motions, you can just pretend that these are like vehicles on a street. But H plus is a little bit like, nah, sometimes it behaves very quantum mechanically. Now let me give you an example. Okay, let's take O2. Okay? Now, here's what happens. The protons in water can tunnel. They can tunnel to another water molecule. So what happens is, it pops over there. This bond breaks and it pops over there. Now, the reason this is quantum mechanical is that it's tunneling. The OH bond is relatively strong. It's about 10 kT, say, at room temperature. Right now, of course, if you heat up a water molecule enough, it will fall apart, but everything will. So at room temperature, OH bonds are strong, they don't break. But you know what, in water, they break all the time, and that's actually tunneling. Now guess what happens when this comes over here? Get this, you're gonna love this. This proton goes there, and then this proton goes back over here. The hydrogens are just moving around like a little circuit. It's crazy, and it's purely quantum mechanical. Now the reason it matters is that it messes with pH. And it messes with biomolecules. Biomolecule structure, which is horribly important. You know prions. You guys know prions?
Yeah.
Well, all right, prions are just normal proteins, but if they get misstructured, bad cow disease. The things that can cause proteins misstructure is pH. This means that you don't really know pH that well. Quantum mechanics kind of messes with pH. It messes with protonating proteins in ways that your Henderson-Hasselbalch equation don't predict. And if they get messed with enough, they change structure. If they change structure enough, they turn into prions. If they turn into prions, you're going to die. You got mad cow disease. So anyway, now again, I don't think I'm not going to mention this on any exam. I'm just saying that one of the things that is on the forefront of like research in physical chemistry is modeling nuclear wave functions. And again, it's a really weird thing because 95% of the time you can treat them like a car, except for H+. It's like the only thing you can't, but guess what is like one of the most important things ever? H+, because it messes with the structure of proteins, and that's what makes you. So anyway, let's just move on. Kind of just blabbering and not really showing anything of any substance. Okay, a question?
It is like how the protons in water, like how they move around like in a cyclic nature. Is that what gives it like cohesive nature? Like why water like comes together?
Hydrogen bonding is what gives water most of its properties. This is just kind of a little nuance that causes things to get protonated, like lysine, right? Lysine's a base. It's an amine. The R group, which is what distinguishes amino acids from each other, is amine. And what you find is that, depending on the circumstances, where is the lysine, you may find that it's protonated when you normally don't think it should be. And you know, biochemists sometimes, when they find this kind of stuff, they'll sit there and drive themselves crazy trying to figure out why, and the answer is because of tunneling. And biochemists don't take quantum, so they don't know that. So sometimes you see people spend maybe even years trying to answer something and that they just can't. And literally, someone like myself, this has literally happened. Not quite this example, but I have sometimes gone to a poster session. Actually, I was reading a paper just the other day, and someone said, I have a molecule that's magnetic and it shouldn't be. And they wrote a whole paper with this wacky explanation. It's an unbelievably simple explanation. They didn't know it. I'm going to write to them and tell them, oh, by the way, you didn't parameterize your calculation correctly. In these types of molecules, you have to put a parameter in your calculation that explains this. You didn't, and the person wrote an entire paper which is completely wrong. I mean, so this stuff happens. Again, it was actually a quantum mechanical calculation where what happened, I'll tell you a little bit about what happened is, remember I was doing this last time? I was doing this, and what happened was the person told the calculation to pair electrons always. And what I'm going to tell him is that he should have told the program not to necessarily do that. And had he done that, what would have happened? What would have happened is this would have happened. The electrons would have split apart. He just didn't know that. Because he parameterized it to only pair, it only paired. It did exactly what he said, but he shouldn't have. It's an incredibly rare thing that this is, right, now you know this is not the ground state, right? It actually is, for a very unusual explanation, and actually I'll even talk a little bit more about that in about a week. But anyway, so you run into these kinds of things where, and you know, I mean, I know about quantum mechanical examples because, I mean, look what I'm doing right now, right? And occasionally I do see people labor for months or years, and I swear to you, I actually feel bad about this. I'm going to write to this guy and say, hey, like, fella, you should have put a 3 where there's a 0, and everything would have been perfectly understandable. Anyway, okay, blah, blah, blah. So, moving on. Okay, this is the hard part. I'm going to write out the Schrodinger equation for the hydrogen atom. It goes across the board twice, so however you write these things down. I don't know how I'll put this on a test. Now, what I'm going to do, now here's my point. So I'm going to write MELEC, mass electron, because you know that there's an M quantum number. So I'm going to write MELEC to make sure that you know that that's the mass of the electron. But based on what I just told you, it's actually, the way you do this properly, the mass of the electron, when you solve this thing, you actually use a slightly bigger number. You remember, you know why? The thing I just said 5 minutes ago? Because you have to use center of mass coordinates, right? So the problem with what I had just erased, wherever it was, with the fact that nuclear electron motion are coupled, you use center of mass coordinates. So what that means is that you don't actually use, you use a reduced mass, right? So the mass of the electron in the Schrodinger equation for the hydrogen atom, you actually use a number that's like 2% bigger, and that accounts for the fact that there's actually a nucleus moving as well, too. Anyway, now again, I'm not going to harp on that, but talk about stupid things people do. I was actually, when I was doing one of your homeworks, I was writing down like the equation for the energy from that we're about to do, actually probably on Monday, and I kept getting a number that was 2% off because I was using the wrong mass. I was using the mass of an electron, and I should have been using, like I say, a little bit of a reduced mass, which is slightly higher. Anyway, just wanted to point that out in case you ever run into that. I'm not going to harp on that because it's a detail that's so nuanced that I don't want you just trying to remember little factoids. Okay, now this deal, of course, is, hopefully this isn't too mind-bending to you, dx dy dz, O squared, r theta phi, here you go. Here's the radial part. Okay, now, I don't remember, I think I may have shown this one point. Remember what that is? Yeah, this is the angle part. So I'm going to actually take this and then I'm going to write this down here. So heads up on that. This is the angle part. This is r squared. R squared. This is the angle part, so I'm gonna deal with this below it, and of course that goes across the board too. Okay, so again, kinetic energy, and these are the angle bits. Now, of course, we're gonna pray that there's a radial, a phi, and a theta wave function. And, okay, kinetic energy. Then we've got Coulomb's law. No, is that R? No, it's R. Force is R squared, energy is R. I forget those a lot. Like when I'm solving, sometimes I actually do like Newton's equation type calculations, and I have to remember that that's R squared. Okay, and since I'm writing out all these freaking wave functions, and I may not be writing them in the same order, not that that matters. Okay, there you go. Remember, this is only half of it. I told you. I remember at the very beginning of 342, I will be writing an equation across the board twice, and that's today. Okay, this thing, right? Now I have to do this on that, and I'm going to write that below here. So you see how I've done that, right? Okay, now what's that part? Let's see. Yeah, I don't want to say too much, right? Kinetic energy, potential energy. I mean, it doesn't look that bad, right? That's the potential energy. Remember how all of this got hard when we introduced potential energy? Because everything was a freeway. Everything was e to the IKX. I introduced potential energy. Wasn't too terrible. It got harder. And this SOB, this thing's a nightmare. I've actually had to do all this angular bits. I had to do all these 2D, 3D rotor, sine, dd, sine, dd, sine, blah, blah, blah. I had to do that because 1 over r, because the Coulomb potential is radial. Because the Coulomb potential is due to radius, that is why I had to work in spherical coordinates. Do all that spherical harmonics, and here we are. Oh, okay, speaking of spherical harmonics. Okay, so now I'm just doing this, so hopefully don't get lost on your, oh, no, I want to make sure you don't get messed up with what I'm doing here. Okay, so I'm doing all this, including the wave functions. And, okay, so this is minus h bar squared over 2 mass. And I, for some reason, wrote mass fully out. I don't know why. That's what I did. Okay, the radial, oh, yeah, let me try to make it neater. The board will blow up. Okay, the radial part will pop out of the wave function, right? And just like the wave function will pop out of the, remember these are little walls. The phi guy stops the phi wave function, doesn't stop the theta wave function. R passes through all the walls, of course. Okay, and you know, of course, we're going to talk about separability. I told you, you never get away from that. Okay, and then, now remember, one thing that always kind of throws me off is whenever I'm talking about the theta guy, because you know how I threw a bunch of questions at you when I tended to break up all those angular bits. Sometimes it's 1 over sine, and sometimes the sine's on top. That's when I'm separating it, right? So this is the non-separated form, just in case you get a little bit. If you've been noticing that sometimes at the front, sine's on bottom or sine's on top, that's before and after separation, by the way. Okay, then there's all this. Okay, the theta thing, which is a little bit, okay, this is just for constants. And then, of course, I get, what I'm going to do is say that I'm hoping that I can just have a rotational energy that'll contribute to the total energy. That's kind of the idea. Oh God, what am I doing? Okay. All right. So now I'm going to work on this thing, and what will be my final equation that goes across the board. Nice, huh? Let me point out that I have written a separable wave function, but I haven't really proved it yet. And I meant to try to look this up before class. I had looked it up before, I didn't really get a good answer. I was gonna look it up again and see if I can find a good answer. Let me ask you this, can I separate this thing? Right, so remember, all of these deals have got to have separate, to show you I've acted on the right, I haven't divided by the left yet. Right, act on the right, divide by on the left, and see whether each term is by itself. I haven't done the act on the left yet, but I'm thinking you can do it in your head. This guy will be cool because the angle parts come through it. This part's cool because the angle parts come through it. There's no walls here. These are constant, so it looks like it's okay. So do you think I'm separated? Now remember, I'm looking for usually a derivative, a term, usually with a derivative, that has more than one of the r thetas and p's in it. If that happens, I'm screwed. Huh? You see one? Because I see 1, 2, 3. I see 3. Where?
Can you multiply by sine squared?
Actually, yes, I have a problem here. I have a problem here, but now, remember we ran into, right, I have theta and a phi here, right, so this hoses me. Now remember, I was actually able to, we ran into this at the 3D rigid rotor. I can multiply by sine squared, and that's why this was into a sine on top. So if I multiply by sine squared, the phi guy's cool. This just picks up a sine on top instead of on bottom, and the rotation ends up with the sine theta, which is why the energy funnels into it ends up being separated, and the energy is solved when I do the theta deal. So that's okay, but now I got one more. Where? Every other word.
Are we doing rigid rotor here?
That was one more word.
No, rigid rotor. No, we're not doing rigid rotor.
So how'd you just pull out in ours?
Well, it's not pulled out, it just happens to be there. This is all, I haven't done any funkiness yet. This is all, other than supposing that it's a separated wave function. But no, R is not, it's not a rigid rotor, it's a variable. Right, it's an operator, it's a variable. Now before, I had mass R squared and I just said that's a constant. But now, R is not fixed, that makes us a variable. So do you see your 3 terms with two variables? Here, it multiplies all the angles, right? Or better yet, right here. Operator. And remember, R is basically X. It works just like X, except that it's the letter R. Operators are either derivatives, which are smart and actually operate, or they're dumb, like X, or X is our new R. R is our new X. And so it's still an operator, but it just kind of sits there. This is our problem. We've got an R and all the angles all together. Uh-oh. And if we can't separate it, then there actually really is no way to solve it. Okay, so let me handle this part. So let me tell you what I'm going to do. I am going to multiply by -2 mass electron. Sorry, that's a little hard to see. R squared sine theta squared over h bar squared. Okay, so that's what I'm going to do to this thing. Okay, again, I'm trying to separate it. Now, as I just mentioned, one of you asked about the sine and the phi right here. No, here, Jesus. Theta, phi, bad. Okay, that takes care of it. Okay, so what am I left with? Okay, and then I'm also going to operate on the left by the divide by the wave functions. Okay, and so when I do that, when I divide this by all the wave functions, this guy gets wiped out immediately. This guy gets wiped out here, and then I multiply by sine squared. So I'm just left with. So I'm doing 2 steps at once. So I'm hoping you don't get totally mind blown by that. But there we go, separated. So we're set there. Then Okay, so again, if x squared over x is x, so sine is on top. This gets divided out, but not the theta, because that's stuck there. So when you divide on the left, this guy doesn't get to go anywhere. And I've got, the innards, of course, are not affected because of the walls that are the derivatives. Okay. Then what I'm going to do is I'm going to bring this guy over. I do that because when I multiply by a negative sign, I like to bring it over because it makes it positive. And then, so mass electron, sorry my handwriting is not great. I get obsessed because I hate how there's two m's at this point. M for the phi wave function and then m for mass. R squared sine theta squared E rotational part over h bar squared. Now again, this is very doable. It's just I've done a couple of steps going from here to here, multiplying by this, and then I divide on the lefts, and I didn't write that down, so I hope you don't get lost, but there you go. Okay, now, R's are up here. These guys are cool. We don't have to worry about them. This is our problem. I've got R theta and phi. Okay, here, there's no R. There's no theta, it's all phi. Cha-ching. Almost there. Here, all theta. Here, my host? Yes, I'm host. I couldn't separate it. Okay, so the solution is non-separable. So, now here's two things I can tell you. You just do it anyway. Apparently that's the answer. We're just going to separate the wave functions anyway. Okay, now it turns out that in physical chemistry, we don't just say, oh shucks, let's just do it anyway. The mathematicians won't allow that. Okay, now I don't understand this, and that's why I was trying to find a better explanation before class, but here's what happens. It turns out that it's the R and theta. Those are the two that are stuck. Phi managed to escape. It turns out that because the angles are kind of their own thing, that despite the fact that I couldn't separate it, the results are still separable between R and theta, because theta and phi. So it's kind of like this. It's like the transitive property of multiplication. If theta is separated from phi, phi has to be separated from R. You can't have all of those. So if theta is separated from phi, if phi is separated from theta, and theta is not separated from R, then theta could never have been separated from phi either. That those would not be possible. So you follow me here? Again, it's actually kind of nonsense, so you should be slightly confused because I am. But again, because this guy exists on its own, these things actually are cool. Because if they weren't, I would have never been able to do this to begin with. So that's the idea. I'm sure there's some crazy mathematical explanation that does prove this. Maybe there's some math theorem I don't know about. And even if I did know about it, maybe it would take half an hour to explain. But we've whittled this down, and because of what I just said, despite the fact that I've got a term with two of the deals in it, it's actually still okay. So that's the take-home message. It's rather unsatisfying.
So separability of one variable implies separability of all?
Of two others. And that's, again, because of the angles and the radial part are just, they're like different dimensions, right? They're completely different things. And so again, look, for one, I really don't understand it either. You remember, this is like, the next class is grad school, right? So you've actually hit my limit, especially with this. I actually don't know the answer. I mean, I do know the answer. The answer is that they're separable for a math reason that I don't actually know. Now here's another thing. If you assume separability, guess what? The wave functions are still e to the im phi and sine theta, cosine theta, the spherical harmonics. The wave functions are the same for the 3D rigid rotor as for the hydrogen atom. And then you solve for R and plug the whole bastard into the whole thing, and it's all solvable. So if you here's the thing. what I'm doing here is trying to prove that the wave functions are separable. But it turns out if you just find solutions and they're separated and apply them and it still works, then it still works. Again, as much as this, remember this is the guy on top. What I have done is I've run into a problem and I'm not really quite able to separate it because of this. But for snarky reasons you can. The next proof is come up with a wave function for R, one for phi and one for theta. Find them. Put them into this and see whether it works out. The answer is it does. So the answer is separable. If it wasn't separable, I would not be able to have independent wave functions for all three and ever make this work. So I think another way to think of that is that this whole isolate into miniature Schrödinger equations it's like a Venn diagram. It's proof, but not absolute proof. If you can do it, the solution has to be separable, but if you can't do it, it doesn't mean that the solution still isn't separable. It's a Venn diagram. Right, you see what I mean? All sociopaths are narcissists, but not all narcissists are sociopaths. Same thing. Not all wave functions that are separated are separable, but not all things that you can't separate aren't necessarily separable. Okay. I really can't do any better than that because, like I say, I kind of hit the limit of what I understand, and I've been meaning to try to see. When I've looked it up in the past, the explanation I found was the one I just gave, by the way. And I don't really care for that. I don't like that explanation I just gave. But regardless, and I'm sure somebody will come up with a snarkier one. Other than, like I say, another proof is that I can separate the wave functions and it works, and let me show you how to do that. Okay, so what we do is, if the angles are spherical harmonics. Okay, so what you do is, now on the homework, by the way, on the homework, guys, on the homework, I have you do a couple more spherical questions. It's a little busy work because on homework 7, after you did the little operator deal, I had you do like, oh, here, the spherical harmonic is sine theta e to the I phi, and I had you do some things. I had you do a harder one. I had you do a D function and work the radial kinetic energy. It was a little busy work, but I want you to get really used to it. So anyway, so you're used to spherical harmonics. It's always like sine or cosine theta, e to the I phi, e to the 2I phi. Anyway, so spherical harmonics. All right, now if the spherical harmonics are true, then what you have is minus h bar squared over 2 times the mass of the electron, 1 over r squared, angle deal, psi of the angles is equal to h bar squared over 2 times mass electron over r squared. I told you this is a bear. L times L plus 1. Oh, wave functions. Actually, I meant to give myself enough room to continue with that damn thing, and I didn't. Anyway. Okay. So, by the way, heads up, I just wrote this. You've already seen this. This is the spherical, this is the 3D rigid rotor. I just wrote it again. I just wrote it with mass r squared. I used to write it with I, but since r isn't fixed, I didn't write it with I. That's the only difference. Now, remember, now I always hate this L times L plus 1. I freaking hate this thing. But I remind myself that it's kind of like h bar squared, free wave, h bar squared k squared. 2D rigid rotor, h bar squared m squared. It's the same thing. It's just not quite L squared. It's L times L plus 1. It's basically L squared. It just comes out a little different because you're in 3 dimensions. All right, so anyway. Okay. This term pops up into there. Oh, God, I'm already confused. Here, what do I want to do? Let me tell you what. Let me take this thing from the top. Yeah, I can do this. This will make sense. Maybe in your notes, I'm kind of cheating right now, maybe in your notes rewrite the thing on top, and I will then, I'm going to insert this L times L plus 1 for here. That's what I'm doing. That was actually the whole point of what I've been rambling on for about the past half an hour. Is that despite the fact that you can't separate, you just do it anyway. And I'm going to plug in everything I just wrote for the angle bits. So the angle bits kind of go away. Okay, so what I ended up, and now I'm also going to do separability. So plus separate, so what you end up with is, so I'm going to divide the radial part on the left, write this stuff out, and then again show separability. I've already done that. Actually, this is, you know what this is good for? When you write out the wave functions this way, the Schrodinger equation this way, it ends up being of a proper mathematical form that you can then look up. So, okay, so I've applied the wave function. I'm going to take care of this guy with the L times L plus 1. This guy has now been hit by the wall. I'm dividing on the left. So anyway, where am I at? Actually, if you recall in cylindrical coordinates, this ends up being 1 over r. So it's kind of neat that the radial part is almost identical, whether you're in spherical or cylindrical, except that instead of in that second term, instead of 1 over r, it's 2 over r. It's the only way that it's different. I always thought that's kind of neat. But anyway, I'm entertained by silly things. Okay, so you know what? I gotta actually have 2. I gotta have 2 parentheses there. Then I've got. Okay, then this is the part I was just writing a second ago. Here is the angle, like the angle energy. Now, the wave function at this point is separated, so this is just a constant. And then, okay, now let's not forget that. Yeah, so all of this just turned into this. And then this is equal to the energy. Okay, so that's the idea. Okay, so, yeah, that's actually quite seriously, that's really about it. There is a simplification I can do. Tell you what, let me just do one more, do I want to do this? Let me do one more simplification. It turns out that I actually showed you this in the extra hour, I think last Friday, that there is a simplification. There's a way to simplify this operator into a slightly smaller form. So let me show you what that is, and then I'm just going to repeat this next time. In a review fashion. Okay, mass electron. So again, I want to point out that the radial parts here can be simplified. So what I'm going to do here is I'm going to write out the slightly simplified version. Not like simplified wrong, like an approximation. It's actually, yeah, so all these radial parts right here, all those radial parts, I usually put this on the test. That's actually this operator right here. A double derivative plus 2 over r derivative is actually equal to this. Then I've got this deal times L plus 1. I'm actually writing this out more like a Schrodinger equation. So I'm kind of unpacking. I'm unpacking the wave function on the left. And I'm trying to write it out like an eigenvalue equation. There we go. Right. So what I did here was, and again, I'm going to write this down because I know I'm rushing a little bit. So again, this SOB on top, you should know this. This is kinetic energy, separated, yada, yada, yada. Here is separated. The angle parts just turn into this. This guy is really this, and I actually showed you that before, but I'll do it in the first part of Monday. And then what I've done is I brought the wave function over to the right. so that you see the operators acting on the wave function equals to the energy times the wave function. So now, so mathematicians like to see it this way, by the way. If you're trying to find an answer in a 18th century textbook, this is what you're looking for. But now this is the eigenvalue way that I've showed you how to do. So hopefully this, whichever one you're more comfortable, these are the same thing. Hopefully you're a little bit more comfortable with this guy here. And what we'll do next time is we're going to start throwing in wave functions. You see that again, you know what's important is, as I said, and hopefully you're sick of this, I've whittled the Schrodinger equation down to miniature Schrodinger equations, get rid of phi, get rid of theta, and I'm left with R, and energy, the most important thing that we ever really want this for, right there. It's the R wave function that solves it. Oh, by the way, you end up with an n quantum number in the solutions, and remember where you see n? You know what n is? No.
Oh, the
Right.
orbitals.
Right. It's the thing that, right, n equals 1, 2, they're the rows of the periodic table. The periodic table is constructed become entirely from this. This is where it comes from. Okay, guys, I talked over it as I always do. 10-minute break. I know there's problems on all this stuff, and we'll fix it. But I'm going to show videos of wave functions. It'll be really fun, so I really hope you come back.